Welcome, everyone. Thank you for coming. So, first session of the morning. What did everyone think of the rabbi's talk? Good? Yeah. It's second time I've seen it talk. It's excellent. This talk, however, is functional PHP. You're all in the right room for that, right? Okay, good. My name is Larry Garfield. You may know me online as Krell. If you want to make fun of me on Twitter during the session, that's where you do so. I highly encourage it. I'm a senior architect with Palantir.net. We're a web development agency based in Chicago. We work mostly with institutional nonprofits, universities, museums, public radio, hospitals, and mostly but not exclusively with the Drupal content management system. I am the web services lead for Drupal 8, which means, who's worked with Drupal before? Okay, you can blame me for about a third to half of all the changes in Drupal 8. Directly or indirectly. I'm also the Drupal representative to the PHP Framework Interoperability Group. It's kind of like the United Nations of PHP with all the good and bad implications that has. Advisor to the Drupal Association and general purpose lovable pedant. My colleagues at work will tell you that the second half of that at least is very true. So, I'm going to give it a little bit of warning in advance. Some parts of this are going to get a bit heavy. Please bear with me. I'll try to keep them at least vaguely entertaining. Let's start with a little history. Let's go back in time a little to the dawn of modern computing. This is the 1920s and 30s when computer scientists well, I should say mathematicians, are trying to figure out what does it mean to compute things. This is a point in time when a computer was not a device, a computer was a person, usually a woman, whose job was to sit in a room all day and do math. And mathematicians are trying to figure out what does this mean to compute? Conceptually, what are we talking about here? And one of the people who developed a definition of computing was named Alonzo Church. And he developed a system called lambda calculus, which is based on the idea that everything is a relationship between mathematical functions. All of computing is a relationship between mathematical functions. And he called it lambda calculus because mathematicians like to call things a calculus because then it sounds fancy. And lambda because he got really tired of writing out the word function longhand. Remember, this is the 1930s. He didn't have a word processor yet. And so started using the Greek letter lambda instead as a shorthand. So function system, basically, lambda calculus. And this is a way of describing all of computation. Meanwhile, another mathematician over in England named Alan Turing came up with another definition of computation, which he called a Turing machine, because he is somewhat more egotistical than Alonzo Church was, which is, it defines computation as a state machine. It's a series of instructions that are changing a list of information. You have some list of information, you've got instructions that are changing that over time. And that's a Turing machine. And they published papers on these very close together, one after the other, and like good scientists do, looked at each other's work and said, this looks familiar. And they got together and demonstrated that, in fact, these two systems are equivalent. Equivalent meaning there is no concept or structure that you cannot represent, that can be represented in one that cannot also be represented in the other. It might be more efficient in one, might be more understandable in one, but both of them are capable of expressing all the same things. And in fact, no one in a century now has come up with a way of expressing computation that is more expressive than these two. There are others that are just weird that are equally expressive, but nothing more expressive. So let's fast forward just a little bit to a man named John von Neumann. There's another mathematician, physicist. He helped develop set theory. He worked on the Manhattan Project. He worked on quantum theory. Just another one of these people who's way too smart for his own good that we don't hear about enough. He also was a consultant on the ENIAC project. It's one of the first electronic computers, came out shortly after World War II. The ENIAC, and then the EDVAC shortly afterward, these are real-world implementations of a Turing machine. Now, they were programmed by Screwdriver, but it was a set of state stored in memory, and then you fed a series of instructions into it via punch card that changed that state. This is a Turing machine. But he went a step further than programming by screwdriver, and was one of the people, the one who gets credited for it, but one of the people, who developed something called the von Neumann architecture. The von Neumann architecture is the idea of a stored program. A program is just data. A program is data that you can manipulate, whose job is to manipulate other data. A program is simply a series of steps, a series of instructions that are followed one after another in linear sequence that are altering memory, they're altering state. And one of the things that those steps can alter is what the next step is going to be. And that's how you do branching, that's how you do conditionals. Every computer in the world today is this. Every single computer that you have ever touched is this, under the hood. Everything else on top of it is just abstraction and user experience. This is under the hood, this is all modern computing. And this is the concept of imperative programming. Imperative in the sense of an imperative mood, a command. Go here, do this, say that, print this, write this value. That's imperative. It is a series of very precise commands that are modifying state. State is values that are going to get changed over time by your commands. And the purpose of a program in imperative programming is to alter that state from some initial condition to some ending condition that you want to know about. As I said, this is all modern hardware. Down at the CPU level, everything is just this. Every computer you've used is imperative under the hood. Conceptually, you can think of imperative programming as following a recipe for a cake. You've got a bowl, that's your state. I'm going to pour in milk, I'm going to pour in chocolate, I'm going to pour in some extra sugar, I'm going to pour in butter. I'm going to apply the mix method to it, the mix function to it, and mix it all up. I'm going to put it in the oven, and I'm getting hungry now, sorry. But you're constantly manipulating that same state over and over again, the same pool in that bowl, which in our case is the computer's memory. Step up a little bit to procedural programming, which is really just a slight extension of imperative programming, which introduces this idea of a subroutine, a reusable series of commands or a procedure. And that lets us have structured programming, which are these abstractions around moving data around in registers, like if instead of branch, doing while loops, doing for loops. These are already abstractions on top of what a computer is doing.